The morning of March 4, 1944, brought brittle cold to Horsham Street Faith Airfield in Suffolk, England. Ice crystals formed on the wings of B-17 Flying Fortress, serial number 731, as ground crews swarmed over her in pre-dawn darkness. Inside the operations building, Lieutenant William Owen and his crew stared at a map that made their stomachs tighten. Berlin, 550 miles into the heart of the Third Reich. The first American daylight bombing raid on Hitler's capital. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. But what made German intelligence officers nervous wasn't the target. It was the mathematics. Their calculations said it was impossible. A B-17 Flying Fortress, loaded with enough fuel to reach Berlin and return, accounting for combat maneuvering and weather delays, should be carrying maybe 3,000 pounds of bombs, 4,000 at the absolute maximum before the aircraft exceeded safe operating weight. Lieutenant Marshal Tixton, Owen's bombardier, knew exactly what his aircraft was carrying that morning. 5 1,000-pound general-purpose bombs, 3 500-pound high explosives, and a full load of 50-caliber ammunition for 13 machine guns, 8,200 pounds of ordnance, plus fuel, plus crew, plus everything else needed to fight their way 550 miles there and 550 miles back. The Germans would spend the next year trying to understand how the Americans were doing something their own engineers said violated the laws of physics and operational reality. The Luftwaffe had built its entire defensive doctrine around assumptions about American bomber capabilities, assumptions based on excellent intelligence, sound engineering analysis, and tactical experience against every Allied bomber type from 1940 through 1943. They were about to learn that the Americans had brought something fundamentally different to European skies, not better tactics or superior crew training or numerical advantage, though all those mattered. They'd brought engineering philosophy that prioritized different problems and accepted different trade-offs than anything German designers had considered. The story of how one American bomber defied German calculations begins 3,000 miles away in Seattle, Washington, where Boeing engineers in the mid-1930s were wrestling with a specification that seemed to contradict itself. The Army Air Corps wanted a 4-engine bomber that could carry significant bomb loads to strategic targets, operate at altitudes above 25,000 feet where anti-aircraft fire was less effective, and possess the range to strike deep into enemy territory. Every one of those requirements fought against the others. Heavy bomb loads meant more weight. More weight meant more fuel burn. More fuel burn meant shorter range unless you carried more fuel. More fuel meant more weight. And operating at 25,000 feet, where the air was thin and cold, demanded engines that could still produce power in conditions that choked conventional power plants. Alexander Kartveli at Republic Aviation would later become famous for engineering the P-47 Thunderbolt with a philosophy of overbuilding everything. But in 1935, Boeing's engineering team was already implementing similar thinking for a completely different reason. They weren't designing for combat damage survivability, they were solving thermodynamics and structural load problems that had no existing solutions. The breakthrough came from a technology that most aircraft manufacturers considered too complex, too temperamental, and too expensive for production aircraft. The turbo supercharger, developed by General Electric, used exhaust gases to spin a turbine that compressed intake air, effectively bringing sea-level air pressure to the engine even at 30,000 feet. On paper, it was elegant. In practice, it was a nightmare of heat management, pressure regulation, and mechanical precision. The turbine wheel spun at 21,000 rotations per minute, later increased to 24,000 in the upgraded B-22 model. The exhaust temperatures reached over 1,600 degrees Fahrenheit. The system required exotic alloys, precision manufacturing, and constant maintenance. German engineers had examined turbo supercharger technology and largely rejected it. Too complex, too maintenance-intensive, too likely to fail under combat stress. They focused instead on mechanically driven superchargers that were more reliable and easier to service in field conditions. For most applications, this was the correct choice. But the Germans had never tried to design a bomber that needed to carry maximum bomb loads to targets 500 miles away at 25,000 feet. They didn't have that requirement. Their strategic bombing doctrine focused on tactical support of ground forces and shorter-range interdiction. When they needed long-range capability, they accepted smaller bomb loads as the price of extended range. The Americans were building for a different war, one where the only way to strike Nazi war production was from England, across hundreds of miles of defended airspace, to targets deep inside Germany. Geography dictated requirements. Requirements dictated engineering solutions. And those solutions produced an aircraft that operated under parameters the Luftwaffe's intelligence analysts considered impossible. By early 1944, Luftwaffe intelligence had comprehensive files on the B-17. They'd examined wrecked aircraft, interrogated captured crews, and monitored radio traffic during missions. Their technical analysis of the B-17G model was generally accurate. 4 Wright R-182097 Cyclone engines, each, producing 1,200 horsepower at takeoff. 13 50-caliber machine guns for defense, crew of 10, wingspan of 103 feet 9 inches. Where their analysis went wrong was in the performance envelope calculations. German engineers started with known specifications and worked backward to predict operational capabilities. They knew the B-17's empty weight, 32,720 pounds. They knew its maximum design gross weight, 65,000 pounds. They knew its fuel capacity in various configurations, and they knew the fuel consumption rates for the R-1820 engines. The mathematics seemed straightforward. To reach Berlin from England required roughly 1,100 miles of flight, accounting for the round trip. At the B-17's cruising speed of around 180 miles per hour, that meant 6 hours minimum flight time, probably 7 or more accounting for formation assembly, combat maneuvering, and navigation corrections. R-1820 engines at cruise power consumed approximately 2,200 gallons of fuel for a 7-hour mission. That's fuel weight of 13,200 pounds. Add the 32,720 pound empty weight. Add the crew 10 men at an average of 170 pounds each, plus flight gear, plus ammunition, call it 2,400 pounds. You're already at 48,320 pounds before loading a single bomb. Maximum design gross weight was 65,000 pounds. That left 16,680 pounds of available payload capacity. German analysts assumed, reasonably, that the Americans would use most of that remaining capacity for bombs. But here's where the math got interesting. 16,000 pounds of bombs was theoretical. In practice, you needed structural margins. You needed defensive ammunition, 13 guns firing 600 rounds per minute, consumed ammunition fast, and you needed operational reserves. The Luftwaffe's calculations suggested that B-17 seconds hitting Berlin would realistically carry between 4,000 and 6,000 pounds of bombs, maybe pushing to 7,000 pounds on missions with ideal conditions and minimal ammunition loading. 8,000 pounds to Berlin was theoretically possible if you stripped everything else down, ran right at maximum gross weight limits, and hoped for perfect conditions. But no professional air force would routinely operate aircraft that close to structural and performance limits. The safety margins disappeared. The aircraft became vulnerable to weight distribution problems, control authority degradation, and catastrophic failure if anything went wrong. German defensive planning in early 1944 was built around these calculations. Their anti-aircraft positioning around Berlin assumed bomber formations would be carrying moderate bomb loads enough to cause damage, but not enough to flatten entire city blocks in single raids. Their fighter tactics assumed B-17 seconds would be operating near their performance limits, making them less maneuverable and more vulnerable to attack. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. And their propaganda assured German citizens that while American bombing raids would be unpleasant, the Americans simply couldn't deliver the tonnage necessary to truly devastate German war production. The British night raids were more feared because Lancaster bombers could carry 14,000 pounds of bombs, albeit at shorter ranges and with less precision. What the Luftwaffe didn't understand was that Boeing's engineers hadn't built the B-17 to maximum design gross weight limits. They'd built it to operational reality limits, and those were two very different things. The B-17's actual structural maximum, the point where the airframe would fail under stress, was considerably higher than the official 65,000 pound maximum gross weight listed in specifications. Boeing had over-engineered the load-bearing structures not because the Air Corps required it, but because any competent aeronautical engineer in the 1930s knew that real-world operations would routinely exceed design specifications. Combat aircraft took ground fire, they maneuvered violently, they flew through weather, they operated from rough fields, and they consistently ended up loaded heavier than peacetime testing predicted because combat operations added equipment, ammunition, and armor that designers hadn't fully accounted for. So Boeing built the wing spars stronger than necessary. They reinforced the fuselage bulkheads beyond minimum requirements. They selected materials and dimensions that provided margins above the official ratings. The B-17 could probably survive takeoff at 70,000 pounds gross weight, maybe 72,000, before structural failure became likely rather than possible. But the real secret wasn't in the airframe strength. It was in the engines. The Wright R-182097 Cyclone with its General Electric turbo supercharger was, by early 1944, one of the most refined and reliable radial engines in production. Wright had been building versions of the Cyclone since 1931, 13 years of continuous development, improvement, and field experience. The turbo supercharger system that German engineers considered too complex had been refined through thousands of hours of operation. Early reliability problems had been solved, maintenance procedures were well established, and most importantly, American production quality was high enough that the systems actually worked as designed, consistently, across thousands of engines. This mattered because the turbo supercharger didn't just maintain power at altitude, it fundamentally changed the performance equation. A conventionally aspirated engine loses power as altitude increases because there's less oxygen in the thin air. By the time you reach 25,000 feet, a non-supercharged engine is producing maybe 60% of its sea-level power. The turbo-supercharged R-1820 could maintain close to sea-level power all the way up to 30,000 feet. That meant a B-17 at 25,000 feet was still producing nearly 4,800 horsepower total from its four engines. Enough power to maintain cruise speed even with a heavy bomb load. Enough power to climb if you needed altitude. Enough power to maneuver if you got jumped by fighters. German bombers at similar altitudes were operating with significantly degraded engine performance. This wasn't because German engineers were incompetent. It was because they'd made different trade-offs based on different requirements. Their bombers were designed for different missions. The Americans needed something no one else needed, so they built something no one else had. By March 1944, crews like Lieutenant Owens were routinely taking off from English airfields at gross weights, exceeding 67,000 pounds, sometimes pushing 68,000, 8,000 pounds of bombs, full combat ammunition, maximum fuel. The aircraft handled it because Boeing had built margin into every critical system. The wings generated enough lift, the engines produced enough power, the structures absorbed the loads, and the pilots learned to fly heavy aircraft that demanded longer takeoff rolls, gentler maneuvers, and careful attention to weight distribution. What looked impossible on paper worked in practice because American industrial capacity and engineering philosophy had produced an aircraft that exceeded its own specifications. The B-17 wasn't operating at design limits. It was operating well within its actual structural and performance capabilities. The official numbers were conservative engineering estimates with built-in safety margins. Real-world operations proved those margins were real. German intelligence was reading the specifications and believed them. American crews were flying the actual aircraft and discovering what it could really do. The gap between specification and capability is where the Luftwaffe's calculations broke down. On that cold March morning at Horsham Street Faith, Lieutenant Owen's crew didn't know they were about to prove German engineering assumptions wrong. They just knew they had a mission brief that said Berlin and a bomb load that made their aircraft heavy on the takeoff roll. The ground crew chief doing the final walk-around counted bombs through the open bay doors. 8,200 pounds. He'd seen the weight and balance calculations. The aircraft was legal, barely, but it was going to be a long takeoff roll. Owen fired up the 4 Cyclones one after another. The turbo superchargers spooled up with their characteristic high-pitched whine, distinct from the deeper roar of the radial engines themselves. Instrumentation showed normal readings across all systems. Oil pressure, good. Manifold. Pressure responding to throttle inputs. The turbo supercharger regulators maintaining correct boost. 7:25 a.m. Takeoff. Owen released the brakes and pushed the throttles forward. 7:31 strained against her own weight, accelerating slowly down the runway. Normally a B-17 would be airborne in around 3,000 feet. Heavy like this, Owen let her roll for nearly 5,000 feet before rotating, using every available foot of pavement. The Cyclones, operating at war emergency power for takeoff, generated 1,480 horsepower per engine, enough to lift 77 tons of aircraft, fuel, bombs, ammunition, and crew into cold English air. They climbed to formation altitude, joined up with the rest of the wing, and set course for Germany. Below them, the English Channel slipped away. Ahead, 550 miles of increasingly hostile airspace. And in the bomb bay, 8,200 pounds of high explosives that German intelligence said shouldn't be there. The raid on Berlin that day involved over 1,000 aircraft, total B-17 seconds, and B-24 Liberators, plus fighter escorts. German radar picked them up over the North Sea, and tracking began immediately. Luftwaffe fighter controllers scrambled interceptors. Anti-aircraft batteries around Berlin went to full alert. But something was wrong with the intelligence estimates. The Americans were approaching in larger numbers than predicted, and when the formations reached Berlin and began their bomb runs, the tonnage falling on German targets exceeded every pre-raid calculation. The first American bombs hit Berlin just after noon, not the scattered harassment raids Germany had experienced before, but concentrated pattern bombing that delivered over 1,400 tons of ordnance on the capital in a single day. The Friedrichstrasse rail station, a critical transportation hub, took multiple direct hits. Surrounding residential and industrial areas absorbed hundreds of tons of high explosive and incendiary bombs. German damage assessment teams working through the rubble over the following days kept arriving at numbers that didn't match their understanding of American capabilities. This much destruction required this many aircraft carrying this much ordnance. But the Luftwaffe had counted the attacking bombers. The numbers were accurate. The tonnage estimates were accurate. What they couldn't reconcile was how individual B-17 seconds were carrying significantly more bombs than their engineering analysis said was operationally feasible. The theoretical maximum and the practical maximum were supposed to be different numbers. The Americans were operating at theoretical maximum, routinely, on missions deep into Germany. By late March 1944, Luftwaffe intelligence revised its estimates of B-17 bomb load capacity for long-range missions. The new figures acknowledged that American bombers were consistently carrying 7,000 to 8,000 pounds of ordnance to Berlin. How they were doing this remained unclear. The revised estimates simply noted observed reality and updated defensive planning accordingly. What the Germans never fully grasped was that they were witnessing the collision between two entirely different engineering philosophies. German aircraft were precisely engineered machines designed to perform specific roles at peak efficiency. They were excellent aircraft. The Focke-Wulf 190 was arguably the best piston engine fighter of the war. The Messerschmitt 109 remained competitive through constant refinement, but German design philosophy emphasized achieving performance within tight specifications. You calculated requirements, designed to those requirements, and accepted that the aircraft would operate within a relatively narrow performance envelope. This made sense for tactical aircraft operating over shorter ranges with more predictable mission profiles. The Americans, with their vast industrial capacity and different strategic requirements, had designed a bomber that was deliberately overspecified, not because they wanted to waste resources, but because combat operations were unpredictable, and having margin built into every system meant fewer catastrophic failures when things went wrong. The B-17 was operating outside German bomber doctrine because American bomber doctrine itself was fundamentally different. The Luftwaffe's primary bombers, the Heinkel He-111 and Junkers Ju-88, were excellent tactical aircraft designed for shorter-range missions supporting ground operations. The He-111 could carry approximately 4,400 pounds of bombs internally, with maximum external loads reaching 7,900 pounds if you accepted severe performance penalties. The Ju-88, more versatile and faster, carried similar loads but was designed as much for dive bombing and tactical flexibility as for level bombing. Both aircraft had ranges around 1,400 miles, perfectly adequate for supporting Wehrmacht operations across Europe or hitting targets in Britain from French bases. But neither German bomber could do what the B-17 was doing: carry 8,000 pounds to targets 550 miles away, maintain formation at 25,000 feet, and return. The physics didn't work with the engines available to German designers. Mechanically driven superchargers consumed engine power to compress intake air. At high altitude, you lost more power running the supercharger than you gained from the compressed air. The turbo supercharger solved this by using waste exhaust gases, essentially free energy that would otherwise just heat the atmosphere. The exhaust spun the turbine drove the compressed air went to the engine, no parasitic power drain, just thermodynamics and precision engineering. German turbo supercharger research had stalled in the mid-1930s. The technology looked promising, but the materials science wasn't there. The turbine wheels kept failing under the extreme temperatures and rotational speeds. Without exotic high-temperature alloys, you couldn't build turbo superchargers that would survive operational use. America had those alloys. General Electric had been working on turbo supercharger metallurgy since the 1920s. By the time the B-17 entered production, the materials problems were solved, the systems were reliable, and Boeing's engineers could design around a technology that German engineers had abandoned as impractical. This wasn't American technological superiority in any absolute sense. It was strategic necessity driving different solutions. Germany's bomber doctrine didn't require extreme high-altitude, long-range performance. America's did. So American industry solved problems that German industry never had to address. The result was an aircraft that operated in a performance envelope. German analysts couldn't accurately model because they had no equivalent platform to use as reference. When Luftwaffe intelligence estimated B-17 capabilities, they were extrapolating from known German bomber performance and making reasonable assumptions. Those assumptions turned out to be wrong. By April 1944, the pattern was unmistakable. American raids on Berlin were consistently delivering tonnage that exceeded German pre-raid estimates. On April 29, 580 B-17 seconds and B-24 seconds reached Berlin and dropped over 1,400 tons of bombs. Each B-17 that made it to target was carrying close to its maximum capacity. German flak batteries around Berlin were positioned and supplied based on expected ammunition requirements. Those calculations assumed moderate bomb loads per aircraft. When the Americans showed up carrying maximum loads, the defensive preparations were revealed as inadequate not because of poor planning, but because the planning was based on incorrect assumptions about American capabilities. The Luftwaffe's fighter tactics had similar problems. German fighter pilots had extensive experience against British bombers and had developed engagement techniques optimized for those threat profiles. When they attacked B-17 formations, they quickly learned that the American bombers could maintain formation integrity and defensive fire even while carrying heavy loads. A Lancaster loaded to maximum capacity became sluggish, vulnerable to fighter attack if caught without escort. The Luftwaffe had learned to target heavily loaded bombers during climb-out or on the return leg when fuel depletion shifted weight distribution. These tactics worked against British night bombers. They worked less effectively against B-17 seconds because the American bombers weren't operating at the ragged edge of their performance envelope. A B-17 at 68,000 pounds gross weight was heavy, but not critically so. The turbo-supercharged engines still produced adequate power. The control authority remained acceptable. The formation could execute defensive maneuvers. German pilots reported engaging B-17 formations that seemed impossibly capable. The bombers maintained tight spacing despite obvious battle damage. They returned fire aggressively. They didn't break formation under attack the way overloaded bombers should. The Luftwaffe's intelligence reports noted these observations but struggled to explain them. The answer was engineering margin. The B-17 had more structural strength than its specifications suggested, more engine power than German calculations predicted, more operational flexibility than comparable German aircraft, not because American engineers were smarter, but because they'd solved a different problem than German engineers faced. Lieutenant Owen's crew completed their Berlin mission on March 4, 1944, and returned to England with battle damage, but all crew members alive. Their B-17 had performed exactly as Boeing's engineers intended. Heavy bomb load delivered to distant target. Aircraft survived flak and fighter attacks. Crew brought safely home. This was repeated across hundreds of missions through 1944 and into 1945. The 8th Air Force, based in England, flew increasingly larger raids deep into Germany. B-17 seconds and B-24 seconds operating at gross weights that German intelligence had classified as operationally unrealistic. By February 3, 1945, American bomber operations had evolved to a scale that would have seemed impossible just 2 years earlier. On that day, over 1,000 B-17 seconds attacked Berlin in what would become one of the war's largest single-day bombing raids. Each bomber carrying substantial ordnance, the raid delivered over 3,000 tons of high explosives and incendiaries on the German capital. The cumulative tonnage falling on German cities by early 1945 was staggering. Between January 1944 and January 1945, Allied bombers had dropped over 45,000 tons of bombs on German targets. The B-17's ability to carry maximum loads on long-range missions was a significant factor in achieving these numbers. German industrial production, which had actually increased through 1943 despite earlier bombing campaigns, began to falter in late 1944, not because any single raid was decisive, but because the sustained weight of ordnance exceeded Germany's capacity to repair damage and maintain output. This was exactly what American strategic bombing doctrine had predicted. Not that individual raids would break German will or destroy single critical industries, but that sustained pressure, delivered in sufficient tonnage over sufficient time, would degrade Germany's entire industrial capacity simultaneously. The B-17's performance characteristics made this strategy feasible. Without the ability to deliver heavy loads to distant targets reliably and repeatedly, the tonnage requirements couldn't have been met. The Americans would have needed either more aircraft or acceptance of lower overall destruction. They got neither. They had exactly enough aircraft, carrying exactly maximum practical loads, achieving exactly the strategic effect that planners had designed for. It worked because the engineering worked, and the engineering worked because American industrial capacity had produced solutions to problems that seemed unsolvable with existing technology. The turbo supercharger was the key. Everything else, the structural margins, the operational procedures, the crew training built on that foundation. Take away the turbo supercharger, and the B-17 becomes a very different aircraft, still capable, but limited to shorter ranges with smaller loads. Not capable of the sustained deep penetration missions that characterized the strategic bombing campaign. German efforts to counter the B-17 evolved throughout the war. Fighter armament increased, with heavier cannons designed to knock down bombers with fewer hits. Luftwaffe tactics shifted from individual attacks to mass formations designed to overwhelm defensive firepower through concentration. Anti-aircraft defenses around critical targets were reinforced continuously. All of these countermeasures had some effect, B-17 losses remained significant throughout 1944, but none of the countermeasures could address the fundamental problem. The Americans could deliver more tonnage more consistently than German defenses could prevent. The mathematics of attrition favored the side that could replace losses faster. America produced 12,731 B-17 seconds during the war. Germany couldn't shoot them down faster than Boeing, Douglas, and Lockheed could build them, and each B-17 that reached its target was carrying more bombs than German intelligence had thought possible. The psychological impact on German defenders was significant. Anti-aircraft crews and fighter pilots, who'd spent months engaging American bombers, developed a respect bordering on resignation. The B-17 seconds kept coming, heavily loaded, flying high, and there were always more. German civilians in targeted cities experienced the bombing campaigns as an inexorable force. The tonnage kept increasing. The raids became more frequent, the destruction accumulated, and there was no apparent way to stop it. This wasn't inevitable. Earlier in the war, when B-17 seconds lacked fighter escort for deep penetration missions, losses had been unsustainable. The October 1943 Schweinfurt raid had cost 60 B-17 seconds in a single mission. Loss rates that high would have ended the strategic bombing campaign. But by early 1944, long-range escort fighters, primarily the P-51 Mustang, had solved the escort problem. B-17 formations had fighter protection all the way to Berlin and back. Loss rates dropped to sustainable levels, and the bombers' ability to carry maximum loads meant that each raid delivered maximum destruction. The combination of heavy bomb loads, high-altitude performance, long range, and adequate fighter escort created a capability that Germany couldn't effectively counter, not because any individual element was revolutionary, but because the integrated system worked reliably at scale. This was American industrial warfare at its most effective, not brilliant individual innovations, but competent engineering executed with massive industrial capacity. The B-17 wasn't a wonder weapon. It was a practical solution to a specific strategic problem, manufactured in quantities sufficient to achieve the desired effect. By April 1945, as the war in Europe approached its end, the strategic bombing campaign had achieved most of its objectives. German industrial production was severely degraded, transportation networks were disrupted, petroleum production had collapsed, and German fighter defenses had been ground down through sustained attrition. The B-17 had been central to this achievement. Not alone, the B-24 Liberator, RAF Lancaster, and other heavy bombers all contributed significantly, but the B-17's combination of reliability, survivability, and load-carrying capability made it the workhorse of the 8th Air Force. The final accounting was stark. B-17 seconds had dropped over 640,000 tons of bombs on European targets. They'd flown over 290,000 combat sorties. They'd delivered tonnage to targets that German engineers had calculated were beyond American bomber capability. Those calculations weren't wrong in principle. They were wrong in execution because they were based on incomplete information about American engineering capabilities. The Luftwaffe's intelligence was excellent on most topics. They accurately assessed aircraft specifications, correctly identified strategic objectives, and generally predicted American operational patterns. Where they failed was in understanding that American industry could solve problems that German industry had abandoned. The turbo-supercharger wasn't secret technology. German engineers knew it existed and understood its theoretical advantages. What they didn't grasp was that American metallurgy and manufacturing precision had made it practical. This was a broader pattern in the technological competition between American and German aviation. Germany often had more advanced theoretical concepts: jet engines, swept wings, rocket-powered interceptors. These were genuine technological innovations where German engineers led the world. But theoretical advantage didn't translate to operational capability quickly enough to matter. German industry couldn't mass-produce jet engines reliably. Swept-wing research didn't produce combat aircraft before the war ended. Rocket interceptors were more dangerous to their pilots than to enemy bombers. American aviation focused on making existing technology work reliably at scale. The B-17 used 1930s aerodynamics, 1920s engine architecture, and World War I-era strategic bombing concepts. None of it was revolutionary, all of it worked, and working technology, produced in adequate quantities, delivered consistently, proved more effective than advanced technology that remained experimental or temperamental. This was the lesson Luftwaffe intelligence learned too late. American capabilities weren't based on superior innovation, they were based on superior execution of proven concepts. The B-17 carrying 8,000 pounds to Berlin wasn't performing beyond its design limits. It was performing exactly at its design limits, which were higher than German intelligence had calculated. That miscalculation, repeated across hundreds of missions and thousands of aircraft, shaped the entire strategic bombing campaign. Robert Owen, the pilot who'd led that first daylight B-17 raid on Berlin in March 1944, survived the war. He flew multiple additional missions, always carrying maximum practical bomb loads, always delivering them on target. His experience was typical of B-17 crews. The aircraft did what it was designed to do. Boeing's engineers, working in Seattle in the mid-1930s, couldn't have predicted exactly how their aircraft would be used a decade later. But they'd built in enough margin, enough redundancy, enough structural strength that when combat operations pushed the B-17 to its limits, those limits held. This was competent engineering at scale, not flashy, not innovative, just systematic attention to detail, conservative design choices that prioritized reliability over performance, and manufacturing quality that ensured design specifications translated to operational reality. The Germans never called the B-17 by any particular nickname in their intelligence files. It was just the Boeing or the four-engine American bomber. They documented its characteristics, noted its capabilities, and updated their defensive tactics accordingly. What they never quite grasped was that the aircraft they were fighting was deliberately over-engineered in ways that their own bombers weren't. German aircraft were precisely engineered to meet specific requirements efficiently. American aircraft were over-engineered to exceed requirements with margin for operational uncertainty. Neither approach was inherently superior, but when applied to the strategic bombing problem, American over-engineering proved more effective than German efficiency. The war ended in May 1945. The B-17 was already being phased out, replaced by more advanced types like the B-29 Superfortress. But for the crucial years between 1943 and 1945, the B-17 had been the primary American heavy bomber in Europe. Its ability to carry 8,000 pounds of bombs to Berlin, while German intelligence said it should carry 4,000, was central to Allied victory. Not decisive by itself, but significant enough that without it, the strategic bombing campaign would have required either more aircraft, more missions, or acceptance of reduced effectiveness. The Americans didn't need those compromises. They had an aircraft that could do the job as designed, and they had enough of them to keep doing it, mission after mission, until German industry couldn't function and German defenses couldn't hold. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now, and don't forget to subscribe.